All right, folks. I'm going to use this as a kind of a lecture format for no slip inclines and torque. So if that's how you want to begin to process the information, if you just want to dig into the problems, and make sure you try some of these yourself and don't just listen, right? So the best way to do this might be to listen to this at whatever speed works for you and then try the problems on your own. So this is a big picture overview of no slip inclines and torque. So occasionally, one of the AP problems, but it was only one of the like 8 that I made videos for today, also requires you to do conservation of energy. So we're going to do a quick review of that. I think that's far easier. So the hint that it's energy as opposed to torque is they're asking you about omega instead of alpha. Or they don't have you draw a force diagram. But the big hint is they're asking you for omega. Because omega has to do with rotational energy. Okay, so just super quickly review and try this on your own if you want. You have, let's say this is a sphere with an I of 2/5 mr squared, begins at rest from a height h. Find the speed of the center of mass at the bottom of the incline. Okay, so mass is changing height. And you're going to say T_me at A equals T_me at B. Don't be confused about the fact that if it is also going to be torque, they're going to tell you what the coefficient of friction is. Remember, it's static friction, and if it's not slipping, you can imagine those gear teeth coming down to meet the nooks and crannies and then rising up. And so they're meshing, they're never sliding across and losing energy. Okay, so energy is conserved. Assume it starts from rest, so you have mgh. Occasionally, they give you the length of the incline, and they expect you to use trig to find the height. I'm going to put that as a hint at the end. But fundamentally, it's mgh. And if you're like, I'm not sure what it is, just say mgh. And at the very, very end of the problem, you can say where h is, and then figure it out. Where h is, oh yeah, h is x stop sign theta. Okay? Don't be afraid to do that. That's a really efficient way to do it. Okay, at point B, I love that. Imagine a LED at the center of mass. It is moving through space in a line. So that means I have a linear kinetic energy term. It is also rotating, otherwise this would not be a hard problem. So you also have a 1/2 I omega squared term. And what is challenging about all of these problems is there's a hidden no slip piece of information that you have got to use or you won't have enough information. Okay, so not slipping means there is a relationship between how it is translating and how it is rotating. And so you have got to use that to reduce variables. So I is 2/5 mr squared, and omega is v over r. Oops, I guess I'm solving for linear speed instead of rotational speed, but once you know linear, you can get omega. Okay, and then you can see that the mass is in every term, but not until you plug in that value for I. And what else happens? This r squared cancels with that r squared. So you get gh equals v squared over 2 plus 4, sorry, the 2's cancel, 1/5 v squared. Okay, so that is going to be a 5/10 v squared plus 2/10 v squared. So gh equals 7/10 v squared. If we care what v is then going to be the square root of 10/7 gh. And then if you wanted to find omega, if that was the question, then omega would just be that over r. Okay, so hopefully energy you really like this should feel comfortable, if not easy, comfortable to you. Like that should not be a tricky AP question. What is tricky, which we haven't done, so I'm only making the people doing the AP do this, is connect torque to these incline problems. So the good news is the force diagram is always going to be the same. Okay, so get really comfortable with the force diagram. It is always going to be the same. In the walkthrough of the AP problems I went through, we must never forget this, but I just stole this from online. Clearly, you have the force of gravity. Make sure you draw that coming at the center of mass. You have the normal force because it's touching a surface, so make sure you draw that coming from the surface. And even though there's no energy loss, there is static friction going up the ramp. Because what would it do without friction? Without friction, it would slide this way relative to the surface, and therefore friction is opposing that and going up the ramp. Okay, this is always going to be the same force diagram. At the end of the video, I'm going to show you that even when it's on the way up, which is maybe counterintuitive, friction is up the ramp. Okay, so the good news is the force diagram is always the same. Okay, so now we're going to apply, wait, I think I have another slide for that. Yeah. So what you might want to do is, what bothers me sometimes is, okay, well, let's just read it. If an object is not slipping, it is translating faster and faster and faster. So you are going to use your linear, you're going to think about the forces linearly to find acceleration. It is also rotating faster and faster and faster. So you need to find an alpha. So what I recommend that you do, whether they ask you for it or not, is draw a torque force diagram where you'll see from the AP problems, they'll say draw every force, make it clear that you draw the force at the point of contact. The reason you need to do that is because your R, in your R of sine theta, is pointing from the pivot to the point of contact. So you have to draw the forces at the right spot to get the right torque. What you might also want to do, this is optional, but what you might want to do, because it will help you realize to use it, this is what you're going to use to do torque equals I alpha. But what you might want to do is say, you know what, the center of mass thinks it's the center of the universe. So I'm going to draw all of the forces as if they are acting on the center of mass. And then remind myself that it is accelerating parallel to the incline. So I'm not going to break down the normal. I'm not going to break down friction, but I am going to break down the weight because part of it is parallel to the incline. That's your mg sine is what makes it slide. And part of it is perpendicular to the incline. That's your mg cosine that makes contact with the incline. And these two forces are always going to be balanced in these kind of problems. Okay, so if you only, by drawing both of these, it will remind you, which we're going to do on the next slide, oh, I have two, maybe three columns. And what's confusing is it's the same object, but for the same object, I'm going to have a torque column, and I'm going to have a linear column, and I'm going to have a no slip column. I highly recommend that you just recognize, okay, this is a situation where things are both translating and rotating. Let me just set up all these columns so I don't get sucked into only thinking about the linear or only thinking about the rotational and then feeling like feeling frustrated. As soon as you realize this thing is translating, oh, let me set up this column. This thing is also rotating. Let me set up this column. It is not slipping. Let me set up this column. The more you'll realize you got something to do. Oh, I'm gonna look at the torques. I'm gonna look at the forces. You're just gonna open yourself up for having everything organized and not getting stuck. Okay. You don't have to draw this center of mass, but it might help you remember that this is really three mini problems that you've got to connect to each other. Okay. So a classic problem is to find the minimum coefficient of friction to not slip on the way down. So I'm just going to make up, you know what, let's just say it's a ring to make our lives easier. Let's say I is mr squared. Okay. And so I already kind of dealt with the force diagram. Linearly, let's call down the ramp positive. And you actually have a linear vertical or perpendicular to the column. And all you have there is that the normal force going up equals mg cos theta. And that's always going to be true on inclines. Again, it's not, you could have an extra force happening, but if we're focusing on torque, they're not going to throw in like a fan crooked or something like that. So the normal is mg cos. But what we care more about is, and that's coming from, some of the forces perpendicular to the incline are balanced. Some of the forces parallel to the incline are not balanced. It's accelerating down the incline. So mg sine theta is winning minus friction equals ma. And then friction is mu times the normal. And then unsurprisingly, the mass cancels. It's all about the mass distribution and not about the mass. So let's clean this up a little bit. We get that the acceleration is g times sine theta minus mu cos theta. Okay, you might solve this for mu because you're like, that's the question, but then we don't know A. And so again, you might feel frustrated and stuck, but if you realize, oh my God, I need 3 columns, and you see these empty columns, then you're like, well, I'm not done yet, so I shouldn't be frustrated because I still got more I could use. Okay, so miscellaneous, it is not slipping. Again, that's not going to come from the force diagram. It's going to come from the wording in the problem that says it's rolling without slipping. So A, which is here that I don't want anymore, is related to alpha and R. Okay, well, I don't really want alpha either, so let's figure out how we can get rid of alpha. And that is in your rotational column. So sum of the torques equals I alpha. Now, the good news is that there is only one torque. The normal passes through the pivot, so no torque. The weight pulls on the pivot, so no torque. The only torque you have is friction. So I'm going to go up where am I? Okay, here. And your lever arm is a vector pointing from the pivot to the force. And then you draw R and F from the same starting point, and you go from R to F. Technically, I'm actually glad I'm doing this. You might not be. Technically, that's negative, so this should be sine of minus 90. But if it's rotating clockwise, then it is translating down the ramp. So since we defined it down the ramp as positive, I'm also going to define clockwise as positive. So I'm going to make that sine of positive 90. So the torque caused by friction is, so the good news is there's only one force, right? R is pretty obvious. F is going to be friction. And technically it should be sine of negative 90, but we're going to make it sine of positive 90 because we want these two things to match each other. So the torque is R times friction, which is mu times the normal. Okay, so remember that. And so it's going to be R mu, the normal is mg cos, because cos is what makes contact, equals I, which I said was mr squared. We said it was a ring, times alpha. Yay, the mass cancels again, and one of the r's cancels. And we want mu, so we don't want to solve this for mu. Oh, and just, I am going to make this a separate warning, but just super quickly as I'm looking at these thetas, don't confuse the theta of the incline with the theta of the torque. The theta of the torque is the angle between R and F, which has nothing to do with this, right? That's always going to be 90 degrees. So be careful. There's a lot of thetas floating around. You need to know which is which. Okay. What are we going to do? Okay, let's plug in alpha equals A over R. Because I was frustrated that I had that extra R, but I see now where that's going to go. So mu g cos theta equals R. Remember, we got rid of one of them. A over R. Yay. My other R is going to go away. So A equals mu g cos theta. Okay, and we don't want A. What we want is mu. And you might say, oh, this is a max-min problem. I see minimum. What's minimum going on there? The key is to not slip. So we want this to be true. And if mu is less than that, this cannot be true anymore. The nooks and crannies can't grab the disc hard enough to torque it around and keep it going. It's going to start to slide. Okay, so I know that that's tricky to think about if you haven't done it over and over and over again. Okay, so I'm plugging this in for A. So mu g cos theta equals g sine theta minus mu cos theta. So awesome, we have even more canceling. G cancels. Doesn't matter what planet you do this on, you need the same coefficient of friction. Okay, so let's get the mu terms all by themselves. So you have mu cosine theta on this side plus another mu cosine theta equals sine theta. Yay, everything's positive now. So we have 2 mu cosine thetas equals sine theta. Sorry for the sloppy handwriting. And let's solve that for mu. It's going to be 1/2 sine over cosine or tangent of theta. Yay, which makes sense. Mu is dimensionless. This is dimensionless. Okay, that is a classic problem. Again, I can't stress enough. It's taken me, 20 years to figure this out, but set up your columns. Otherwise, it just helps you organize what you're doing, and it will help you not get frustrated because you realize I got to fill out all these things. And it'll just help you focus and figure out what you haven't done yet so that you know where to go. I think it'll just make it so much faster. Okay, so that is the minimum coefficient to not slip on the way down. Okay, the point of this slide is that I had to really, really work through and think about the fact that on the way up, the force of friction is also acting up the ramp. So I'm going to draw this bigger. I think this is supposed to be on the way up. I'm going to draw this bigger so that we can understand this. So if it is heading up the ramp, the velocity is up, but you know it's slowing down, right? It's converting the rotational energy into gravitational potential energy. So that means the net force must be down the ramp in order to slow down linearly. Okay, which we've got a downward force. You have mg, and clearly mg sine theta is opposite the motion. So we do have a force that's slowing it down. I think initially my brain also wanted friction to be down the ramp because it should be opposite what it was on the way up, you would think. That would be the case if it were a box. That's why I made this particular slide, because it's a little tricky. So let's figure out what's going on. Let's make this orange. Okay. So if it is going up the ramp, that means that it is rotating this way, right? Hopefully that makes sense, that it is rotating and translating up the ramp. So if it is rotating counterclockwise, in order to slow down rotationally, alpha needs to be clockwise. And that's why friction has to be up the ramp, because we need it to create a clockwise torque. So imagine a bird's eye view of a merry-go-round, and we want the torque to be this way. You would need to push on it this way to make it rotate that way. So friction has got to be up the ramp. And friction is still going to be mu mg cos. Okay. So that's one argument for why friction needs to be up the ramp. It needs to be opposite, needs to create a torque that is opposite the way it's rotating. And then you can skip ahead to the next, we're almost done, we're going to do some hits and warnings. But then I'm like, well, that seems weird, because then it makes sense that here, I'll go back up. On the way down, if it were a frictionless incline, you would just have mg sine. And so the fact that we're subtracting friction means it is speeding up at a lesser rate, right? It should be speeding up at g sine theta, but we're subtracting stuff from it. So it's accelerating, it's gaining speed not as quickly as it should. And that makes sense, because some of that energy is going into rotation, so it can't translate as quickly. So you might think, well, then now it's got to slow down more quickly. The opposite. So the acceleration is going to be mg sine minus friction all over mass. So the mass cancels again. So you can see the acceleration is the same in magnitude as it was on the way up. And so that means it's slowing down slower than it would if it was just a frictionless cart going up the ramp. Because this magnitude is less than if a frictionless cart would just be g sine theta. So it took me a while to figure out what's going on. So what's happening is some of that energy is the linear kinetic energy is being converted to mgh. But what's happening is, as it goes up the hill, it is losing speed because it's gaining mgh, losing linear speed. And since v equals omega r, as v goes down, omega goes down proportionally. So the reason it's slowing down slower than it would if it were just a cart is that as it goes up the hill and slows down, it's converting its rotational kinetic energy. Technically, it's converting the rotational kinetic energy into linear kinetic energy, which is then being converted into mgh. But you don't have to go that deep if you don't want to. It's got this 1/2 I omega squared that is kind of, quote, stored in this like what's called a flywheel. So as it goes up the hill, it accesses that rotational energy to make up for not completely, but that's why it doesn't slow down as quickly, is because it's also gaining, it's got to lose the 1/2 I omega squared, so it's got this thing going up the hill has more energy than this thing going up the hill because it also has the rotational energy. So that's why it's going to take longer to convert all of it to mgh, because it has two forms of energy to convert. All right, So I don't know if that makes sense to you, but if not, like something to think about and ponder. But what I absolutely want you to know, it doesn't show up very often. Most of the times the things are sliding down the hill, but if it does go up a hill, you might be tempted to put friction down the hill like it would be if it was a block. If it was a block, friction would change direction. If it's a rotating object, friction is up the hill. And I know that's tricky, and I had to think about that for a long time. So same force diagram, whether it's up the hill or down the hill. And I'll stop there, and you can come see me if you want to talk about it more. Okay, quickly, some hints and warnings. There are two different thetas. When you break down your weight is mg sine and mg cosine. And that theta is the theta of the incline. But when you calculate torque, we shouldn't use theta, but we do. This is the angle between R and F, which every time I've seen it is 90 degrees. Okay, so different theta from this theta. Hints and warnings number 2, on at least one of the AP problems, they gave you the length of the incline. It might be that after you do the challenging, lots of hidden points acceleration, you need that distance to use physics Sudoku, don't care. It could be that X is to find, if you're doing energy, that X is to find the height, which is X sine of theta, just like breaking down a force. Stop sign is the vertical part. So again, the two reasons they might give you the length is to find the initial height, which is just an extra step, which is kind of a pain in the butt, but that's life. You know, sometimes that's what you know. You go into the lab, you know the length, and you don't know the height. And it could be to do a, position function after you find the acceleration. And okay, and then I already talked about this, so I'll say this quickly. Sometimes there were a couple of these problems after I did all the video answers for y'all. Sometimes they don't even say draw a force diagram. So please do that. I think it's super helpful. But it's from all the ones I've done, they never have you draw two. One so you could focus on torque, and one so you can say, you know what, I don't care about the point of contact. I want to remember that, hey, this is, I can also just think of this like something going down the incline. Okay, so those are the big picture concepts. Hope this was a helpful either introduction or a review. And as always, reach out with questions.